Okay, we're going to look at the geophysics of the flood. What then dipped the tip of the the crust into the earth? What started it all? We don't know. But what happened in our model is that three things occurred simultaneously. And I can't hardly talk about one thing at a time, so I can't talk about three things at a time. But these three things, subduction, mantle-wide flow, and yeah, right, the rising, are all have to happen at the same time. I'm gonna speak of them in sequence. I'm gonna in sequence of three, but you have to keep in mind that they're all simultaneous. And this is the first one I'm going to talk about is subduction. And what subduction is the idea that the ocean crust began diving into that mantle. The ocean crust, which was denser than the mantle, had that opportunity to dive in. Once it did, it did. And that's called subduction. Now, the model at this point is based upon John Baumgartner's modeling of the interior of the Earth. What John did for his PhD dissertation is he modeled the mantle of the Earth with basically a finite element analysis modeling, which we use to, you can only do so many experiments with materials, but you can create computer models that simulate those materials, at least if you describe the materials properly and put the proper information into the computer and build a bridge with it, you can put stresses on the bridge in the computer program and see if the bridge holds up. Rather than build an experimental bridge and then see if it holds up, if you did this right, you could actually design a bridge before you built it that would actually stand up. That's the idea of finite element analysis in materials science. And he was wanting to do that same sort of thing to the mantle of the Earth. Now, what he's going to do here is plate tectonics had already proposed that what was happening was that plates sank into the mantle and that the mantle moved out of the way in a circular fashion, creating circular motion in the mantle, or a flattened circle motion in the mantle. And this sort of motion, simple motion, that can be seen, by the way, if you put a pan of water on the stove and turn on the heat, you can begin to see the water circulate in that pan. That's what we're talking about. The mantle is circulating in that fashion. That was modeled two-dimensionally. You can take a two-dimensional cross-section, and the mathematics for modeling that is fairly easy. But John was wanting to model this three-dimensionally on a spherical Earth. Okay, and that hadn't been done. No one had ever, that was a lot of mathematics, and in fact, it couldn't be done without supercomputers. And so he was kind of early on in the revolution of supercomputers, that he could model the Earth three-dimensionally, the mantle of the Earth three-dimensionally. So the idea was to divide the mantle into a bunch of little boxes. And here is he divides the mantle first into these shapes, and then this smaller and smaller and smaller and smaller. And so he's gets to a point where ultimately he's divided the mantle into something in excess, at this point, an early version of his model, something in excess of 100,000 little boxes. So now what he does, the idea, once he's done that, now later versions he would get more, you could make your pixels smaller by making more boxes, but of course it's harder on the computer, takes longer on the computer, crashes your computer earlier. But early on, his early model was approximately 100,000 boxes. In each box, he has the computer solve a few simple partial differential equations. These four equations are three equations, sorry. These three equations are real simple equations, as you can see. The basic idea is very simple. Here's your box. what comes in has got to come out. And that means what temperature, what heat comes in has got to go out. What momentum comes in, linear momentum comes in, it's got to come out. What rotational momentum it comes in, it's got to come out. It's more or less as simple as that. It's basically saying once you've divided your whole mantle up into all these pieces, you're studying the motions in the mantle, and you just can't keep packing matter into this little box. The matter going in's got to come out somewhere. So he's got to do this in each box simultaneously over the entire mantle in 100,000 boxes all at the same time. This is where it becomes, impossible for the human mind or a simple mathematics. It's where you need the supercomputer to do the project. And here's an example of a supercomputer that he used relatively early on. He first had Cray computers as they were being developed. Then he got to where he used this particular computer in Japan. I mean, this is in a day when we're making computers out of our watches, this sort of thing. We still have computers on this planet that are fill rooms. They are monstrously fast computers, of course, you can imagine. But these are the kinds of things he was using. Now, keep in mind, and this is important to understand, his computer model is so complex, is so difficult, that it crashed the world's fastest computers in only, he could only simulate 60 days of real time. And so he crashes the computers in a half hour in every case. And now, it's been a long time since he started this in the 80s. We've gotten faster computers. But he's a software, he's creating software. He wants things to get better and better, right? So about the time they come up with a faster computer, he's put more boxes in there. So over time, he continues to crash the world's fastest computers in a half hour, and he's never broken the 60-day boundary. He can't simulate more than 60 days of time, which out of a 360-day year isn't bad. 17% of the, but it's not the whole flood, okay? This is just the beginning of the story, or maybe the middle of the story. It's just a little part of the story, but gives us hints as to what might actually have occurred in the course of the flood. And basically what happens here in the model is the crust. So he's going to represent, this is a two-dimensional picture of cross-section of the mantle. He's doing it in 3 dimensions, but you can't see that, So we're just going to take a two-dimensional cut through the mantle. So this is the base of the mantle. Core would be down here. The crust is up there at the top. The red represents the initial temperature of the mantle at various places. So the red down here is not the same temperature as the red up there. The red down here is the temperature of the base of the mantle normally at the beginning of the simulation. The red up there is the temperature of the mantle at the beginning of the simulation. In other words, here it's close to 0 degrees centigrade. Down here, about 1,400 degrees centigrade. Here it's about 3,000 degrees centigrade. So, the red represents the initial temperature. And now what he does is he has a slab on the surface dip down into the mantle. He's going to see what happens to the slab. Here's a slab being represented. It's cold relative to the temperature of the mantle. As it goes down into the mantle, it's got to displace the mantle. You have arrows indicating how the mantle is moving in order for the stuff to go down into the mantle. As it does so, the mantle moves along the side, or the plate slides through the mantle. There is frictional heat that is built up along the sides of the plate. Also, as the plate drops down, and early on, this is a pretty big resolution. It's about 200 kilometers, which is much bigger than the plate really is, but that's the resolution he had initially. It's going to move the mantle material away as it dips down. It deforms the mantle. If you take a rubber ball and squeeze it and deform it, it'll warm up. So deformation of the mantle also heats the mantle. It heats both the mantle and the dropping slab, And the key here, though, is that the material of the mantle and the material of the slab, the viscosity of the mantle is related to is inversely proportional to the temperature to the fourth power. That's really cool. Yeah, you didn't understand. What that means is if you double the temperature, it drops the viscosity to 1/16 the viscosity it had before. So the more you heat it up, the more runny the mantle gets. So as the slab goes into the mantle and heats up the mantle around it and deforms the mantle, thus also heating the mantle immediately around the slab gets runnier, which causes the slab to increase its speed. Increasing its speed heats it up even more, it accelerates. So in his model, the slab accelerates up to about 1 meter per second, or several meters per second. Unlike conventional plate tectonics suggested, where it's only moving at centimeters per year, his slabs are sinking at meters per second. And so rather than continents moving at the rate your fingernails grow, they're moving about as fast as you can run. This is not continental drift, this is continental sprint. Because attached to the other end of that slab that's being pulled into the mantle by its own buoyancy is a continent that's pulled along the surface as fast as the other end of the slab is being pulled into the mantle. And so it stretches and it heats up. You can see the heating in the colors here. And looking at now a cross-section across the entire mantle, some 20 or 30 days into his simulation, he's got, again, now here, these various illustrations by John, he kept changing colors, so it's going to be confusing. But in this particular case, green is the original color, is the original temperature. So, and it's kind of nice because green's in the middle, right? So anything that is going towards the red is increasing the temperature. Anything that goes towards the blue is decreasing the temperature. In other words, sometime after the simulation, it went from green to blue. This area cooled. This area heated up. And so what we see developing, and then we got arrows to indicate motion. Here is a slab that's moving along the surface and diving into the mantle. Because the slab is cooler, it is showing up as a cooling of the mantle. But notice there's some other things that come in. This is the subduction. I can't point out the other stuff yet. This is where the subduction is occurring, and it's occurring over here on the opposite side of the world. Subduction is cooling the mantle. There it's showing up on a simulation. 2 places on opposite sides of the world where subduction is occurring. After playing around with a number of continental configurations, John settled on this continental configuration to start with. And I know this is confusing. There is a thin dark line around the current positions of the continents. So right here is South America, North America, current positions, Africa, current position, Asia, current position, Australia, Antarctica. But we know from the geologic column, there was a time when the continents were together, called the Pangea configuration. And he's starting with a Pangea configuration. So he's got South America tucked up against Africa. India is tucked in there with Antarctica here and Australia here. North America is tucked against Africa and Europe. And that's the Pangea configuration. What John did is had subduction go along the blue here. This is where subduction is occurring in his model. When he allows subduction to occur in those particular places, what happens is that in time, the continents move apart from one another as we think they did based upon geological data. This is really cool, okay? No one had ever created any sort of model that moved the continents in the right direction. Let's take a look at this. Here we have 15 days into the flood, since the beginning of the simulation. North America has split away from Africa, and it's heating up there between the two, because hot material from the mantle is coming up. That's another part of the story. It's occurring at the same time. Here are the direction arrows for North America. Here's the current position of North America. Here's the position in the simulation. The arrows are heading in the right direction. They're heading right straight towards the current position of North America. That's cool. Okay. You've got here's Australia over here in its current position. Here it is in the simulation. Here's the direction the arrows are going, right straight towards the current position of Australia. This is cool. Here is Antarctica. I mean, this was so exciting to everyone. Secular, everybody this was just mind-blowing. Here's Antarctica. Here's present position of Antarctica. Arrows are going straight south. That's where Antarctica is, right? This is cool. Everything is going just exactly the direction. One little interesting comparison. Here's South America. Here's the current position of South America. Position here, the arrows are going this way. That seems to be the one thing that's not going in the right direction. But alas, if you know geology, you get really excited, because we know from geology that the last motion of South America was straight to the north to slam into North America and close the Panama Canal and close the central. So the real direction South America took was to go south and then swing to the north. And here we have the southern motion at the like, yes. And if that wasn't exciting enough, this is what John picked up. John picked that stuff up, and he was excited about it. Everybody's excited about it. But what got me, and I got really excited about, is as the simulation progresses, the length of the arrow indicates the speed. So little arrows indicate things that are moving slowly. Long arrows indicate things that are moving more rapidly. As this progresses, India gets really long arrows. Out of all of them, it almost doubles all the other arrows. And I looked at that and said, that's incredible. We know that India moved faster than every other continent. And so it didn't just move them in the right, and it slams into southern Asia and raises the Himalayan mountains. I mean, it's spectacular stuff. It didn't just move the continents in the right direction. It moved them with the right relative velocities. Mind-bogglingly amazing. This is cool. Okay, this is 15 days into the flood, 20 days into the flood. 20 days, it's moved this far apart. Now, what's also cool about this period of time when John is actually publishing this in the secular literature is he would publish these diagrams, black and white, they weren't as pretty as this, in the technical publications. Off to the side over here, and I blocked it out because it's all messy. You've got all sorts of information there, lots of numbers, and included there was the time, colon. It would be, in this case, 2.5 times 10 to the first days into the simulation. I mean, it's right there. And it's in the publication. It tells you how long it's been since the beginning of the simulation. It would be published in the article with this caption underneath it, with this stuff all here. It says, here's the position of the continents 25 million years after the separation began. I mean, if you look carefully at the publication, it's right there. You can't do this slowly. It doesn't work slowly. It stops completely. Boom. It don't go nowhere. It accelerates into speed, or it doesn't do anything.
I hope you enjoyed this video. Please make sure to hit that like button, it really does help, and subscribe if you enjoy the content and want to see more, and find more of us on our main channel on Team Standing for Truth. This is Matt Man. Until next time.